Hi, this is John Sanders with AWS. This is part 4 in our video series about modernizing applications on AWS. In this video series, our customer, Acme Financial Data Service, has been going through a process of moving their application from a legacy monolith on-premises to modern architecture on AWS. Let's take a quick recap where our customer, Acme Financial Data Service, is at in their journey. In the previous video series, Acme Financial Data Service was able to segment out functionality of their monolithic application. They were able to convert their existing application to .NET Core, and they were able to package and containerize their applications with Docker. Currently, all their data is largely stored in a single database cluster. With the increased load on the account and inventory databases, they've been unable to scale. Data domains should ultimately now scale in relationship to their domains and their application domains therein. Data models are also increasingly diverse, and not one size is fitting all. The goal of this session are as follows. Create a data landing zone where data can be brought in, transformed, and ultimately sent to other data sources. This will enable product teams to curate diverse data models across different data sources that they previously had in data silos. This will also ease in data governance and being able to quickly identify areas of concern of where more security is needed, increase your security posture with encryption at rest across different data sources you previously may not have access to, and have tight-grained controls over sensitive data. The other goal is to democratize data to fit an ever-growing feature set. As customers request new features, the number of different data sources that may be brought in will rapidly increase. This will also enable advanced use cases against structured and unstructured data, such as advanced analytics and machine learning. It will optimize its data performance and scale based on the data's access patterns, not just the underlying storage mechanisms. So quickly, let's look at what Acme Financial Data Services data landscape, see what it really looks like. Currently, all of Acme's data lives in that single monolithic data hub. This encompasses account, invoicing, inventory, shopping, payroll, reporting, and logging. If we dive a little deeper and look at the size of these databases, you'll see that some are similar to each other. And though its size may be an indicator of how frequently accessed this data is, it may be misleading. For instance, the most used systems here are account and inventory. The amount of transactions per second happening within the account system are disproportionate to any other part of the system. And we'll go into in a second why that happens. The inventory system is designed as a ledger system, and thus it must continuously grow over time. Inventory is done as a summation over time, and is restocked by a new entry. For instance, think of it this way. If I get new items, I will add a record to say there are 100 new items. For every item taken out of inventory, I will decrement by the amount to be taken out. Maybe it's 1 or 2 items, and that will build over time. At no given time can I truly prune those records. I ultimately must have a record in there as a stop record, meaning it will take the previous amount, sum them up, and that is my new record, and I can delete everything past that. But that's a labor-intensive process. The account, as mentioned earlier, it's not as large as some of the other databases, such as reporting or inventory. Yet, every request hits the accounting system. And we'll go into a little bit more use cases later. If you look at the reporting database, it's large. It's 48 gigs. And is a star schema that is built for reporting. And a scheduled job runs at 3 a.m. to update the report. We could probably take this further, which we'll explore in the next use case. So let's talk about some characteristic issues that we're identifying here. You have account as an object style with relationships. There's edges to the different types of accounts. For instance, a profile may have a connection to a credit card or a relationship to account update and account audit history. The inventory, as mentioned earlier, is a ledger style system. And this is why we want to separate these databases to begin with. The residence within this database makes it dramatically difficult to scale and is ultimately only feasible to scale vertically. You can partition, shard, replicate, co-locate data, yet you still have to decouple between the schema, compute, and storage to ultimately scale. Because of all these diverse characteristics, each database will scale differently. Let's think about that for a second. The ledger system will scale differently because, remember, it builds over time. The account system will scale based on the number of users that are in it, which is a different scaling characteristic. The reporting will scale based on the amount of data that we want to generate reports on, or the types of reports we want to curate on. So, to ease the pressure on this database and to scale elastically with our users and our backend systems, Acme Financial Data Services needs to move inventory and the account database somewhere else. And as a bonus, it'd be nice to move the reporting database to something else that was more purpose-built for this. Acme Financial Data Service has been trying to get streaming data and near real-time reporting, not the 3 a.m. batch process. So now that we know the issue, we need to target the data characteristic to use. As mentioned earlier, the account is a single unit. It's a person. It's a thing. The inventory is clearly a ledger, and it increases and decreases for unit or item. Reporting is temporal in nature, as data changes over time. So now let's get into how we're going to solve that issue. What ADFS will need to set up is a data lake. Now that we have so many choices on how to load and sync and migrate data, let's talk about where it gets stored and how ADFS will organize, manage, and prepare its data for analytics and purpose-built databases. The data itself will be stored on S3. S3 is an object storage with 11 nines of durability and will meet ADFS's security requirements for encryption at rest and in transit, as well as for DR and cost control requirements. We will also use this to start a data democratization effort, which will accelerate ADFS's move to purpose-built databases we will cover in the next module. Lake formation will set up a secure data lake with a data catalog, ETL transforms, also known as extract, transform, and load, and security controls, all within a matter of minutes. We will also use Glue to manage our ETL process for ADFS using their existing Spark scripts. As a definition, a data lake is the new information hub. It's a central, secure repository that enables you to govern, discover, share, analyze structured and unstructured data at any scale. And as the amount of data accumulated for ADFS, they store their data in different silos, making it difficult to do analytics and enhancements. To make it easier, ADFS will want to move their data. To make it easier, ADFS will want to move their data into a single repository, thus a data lake. Well, why should we be looking at a data lake? ADFS will need to store their data securely at any scale and at low cost using standard-based data formats of their choice. ADFS will need to find a way to analyze their data in a variety of ways, using a broad set of analytic engines, ensuring their needs will be met for their existing and future analytics use cases. And it will also enable them to move towards purpose-built DBs in the next module. ADFS will also need to go beyond insights from operational reporting and historical data to being able to perform machine learning in the future in real-time analytics to accurately predict future outcomes. While we won't cover machine learning integrations in this module, enabling ADFS to land their data in a central data repository such as S3 unblocks data scientists within ADFS to use high-level ML services such as Comprehend for sentiment analysis and Forecast to predict inventory more easily. This also puts machine learning and AI services in the hands of developers, product, and data scientists. The data scientist could use SageMaker for experimentation, development, training, and deploying of custom purpose-built ML models that give ADFS an edge in their industry. These all were constrained by having data silos, which made it difficult to correlate across those silos, trace data lineage, and curate data for new and innovative products. With using Glue as part of our pipeline, we want to target the three databases we mentioned earlier: account, inventory, and reporting. The pipeline underneath Lake Formation, which we will use, looks something similar to this. We'll want to create a catalog, which is essentially tables that are assigned to a database. Account has tables, inventory, reporting, etc. That catalog gets stored in the Glue catalog, which is our central metadata repository. Glue also includes an ETL engine that will automatically generate Python or Scala code and can be used to ingest transform data. Lake Formation will automatically do this for us. We will then ingest using standard JDBC or ODBC data sources today. The ODBC driver we'll be using is to connect to SQL Server in our data hub. Glue crawlers automatically update the metadata store as new data is ingested. The data in the consumption layer is used by analytics teams for serverless analytics such as Athena or Redshift, our data warehouse, which we may land in the future. It will also be used to consume data into our purpose-built databases in the next module. Landing the data in S3 then begins to democratize the data for ADFS. This enables them and their engineering teams to come up with new innovative products across the entire organization's portfolio versus the individual data silos that were defined earlier. Now, going into what Lake Formation is and what it will set up that pipeline for us, Lake Formation encompasses 5 separate pieces. Glue, which we talked about earlier, which is our managed ETL process. Blueprints, which point to a specific database type and handle the extraction for us. ML transforms, which can use machine learning to do deduplication. The data catalog, which is metadata about the tables, types, and locations of the data that is living in S3, as well as access controls around who and what can access specific pieces of data. All of this is set up for us with Lake Formation. So the next question is, how do we load data in using AWS's SQL Server? Right now it's living on RDS. RDS can be a target for Lake Formation. There are 2 ways we can do this with the blueprints. We can decide we want to do a one-time migration or incremental using change data capture. Considering the different tables that we'll be using, account, inventory, and reporting, we'll want to use a combination of the 2, depending on the use case. For instance, with accounts, we could do one shot. With inventory, it may be incremental as it's changing over time. And the reporting also could go back to one shot or one shot at a periodic basis. There's other information we can bring in, such as Kinesis Data Firehose for streaming data, CloudTrail, Elastic Load Balancing Logs, or CloudFront. While we won't cover those immediately in this module, it's important to point out that streaming data, or data that's changing rapidly over a period of time, is also a target for a data lake and can be handled accordingly. A good use case for this would be as data changes in SQL Server, we push those changes into a stream so they can be processed in near real time by another data store and or landing in S3. Think about it this way. If we have an account that is changing in our original data store in SQL Server, and we want to process that record in near real time into our now purpose-built database, that is where Kinesis would come into play. We would take the change, push this into Kinesis, use a tool such as Glue or Hadoop, and process that and store it in our purpose-built database. We'll go into that in our next module around purpose-built databases and getting ADFS into there. So a little bit of a definition on blueprints. Blueprints heavily leverage functionality in Glue. We use Glue crawlers and connections to connect and discover the raw data that needs to be ingested. Then Glue generates code for us and Glue jobs for us to ingest the data into the data lake. It will handle the transform and load into S3 for us. Then we leverage the data catalog to organize the metadata. Then the workflows construct to stitch together crawlers and jobs, allowing for monitoring of individual workflows. These individual workflows will be targeted at a specific database so that we can control them independently. These are all natural extensions of Glue's capabilities. Now let's go over and see how we're using Lake Formation to enable ADFS to move the data from those different databases into a data lake. So we're in here in the AWS console, and we're looking at RDS, Relational Data Service. And we have a SQL Server set up that is running Standard Edition, that is running a replicate of the data service that we talked about earlier. So you have one database here. As you can see, it is SQL Server Standard Edition. If I drill into that, there's one active session. And we'll go into what that active session is in a little bit. But everything here is standard configuration. Let's hop over to Lake Formation and see what information Lake Formation was able to pull out once it was set up. Now if we go into the ADFS database here, you'll see it's pointed to a very specific S3 location where the data is being saved. It's actually being pulled out of our relational data service. And we'll go into that in a little bit. Now let me go to View Tables. And what you're going to see is all of these tables that were able to be pulled out of the database. The question is, how was that done? That was done with something called blueprints, which creates a workflow. If we look at blueprints here, this blueprint has run multiple times against our RDS database. That blueprint is exporting the data from SQL Server into our data lake. It can be done as a one-time, or it can be done as a continuous replication. Now that the data is living in Lake Formation, how would we query it? How would we use it in other systems? That's where Athena comes in. So we have the ADFS database that we had previously in Lake Formation. We have all of our tables. So if I go in here, I'm going to look at a specific salesperson. I'm going to use this V. This is a view that is able to pull that information. Going ahead and preview that table. And it's now queried that data. That data is protected by Lake Formation, living in Amazon S3 and put into Parquet format. Parquet format for performance. So as you can see, all the data that was in RDS is now living in lake formation and being replicated up as things change. Now, being replicated as things change from a continuous replication mechanism is done on a timed fashion in lake formation. In lake formation, there is no concept of continuous streaming. We would want to capture those continuous changes out of the database and process them in near real time. That is where Database Migration Service comes in. Database Migration Service can listen for changes inside our relational data store, take the change and replicate it up, either into another data system or into a streaming technology. In this particular case, we have an ongoing replication pointed at a target, and that target here is database 1, which is SQL Server. And the target is a Kinesis stream. Now the target could be another database, it could be a data warehouse. We're streaming it into Kinesis because we're going to use that later to do near real-time transformation into a purpose-built DB based on the use cases of how the data will need to be used for the microservice that we're pulling off. Let's go back into the source database so we can show you how the configuration worked. We have a username. We have a database that we're targeting. We then have a server name and some other connection information. Now let's go over to the migration task that's handling the migration itself for our target. So we have one here called Sales Public. That's an ongoing replication. Let's drill into that a little deeper. If we look at mapping rules, we have a selection rule. The selection rule says only use a schema called sales and only a table name called salesperson quota history. This means that we can have individual migration tasks targeting a single or multiple pieces to replicate on an ongoing or one-time basis. What this will enable us to do is capture changes for this table or multiple tables and process them to our data lake, to another database, or to stream to be handled in a multitude of use cases. Now let's hop over to Athena and show you what else you can do. Now we have a salesperson. I could cross-join to any other table or database that's living in lake formation. For instance, we could query for salesperson and join by vendor or by person, the root object, or by human resource information if we want to do some salary information. Now that the data is living in a data lake and being replicated up, you now have the ability to apply any technique you can think of, be it machine learning, database transformation, database modernization, and advanced use cases beyond that. Now let's recap what we've observed. Acme has now moved their data from SQL Server to a data lake, which has enabled them to query across different data sources and enable a database transformation effort. Acme is also replicating their changes from SQL Server to a stream for real-time processing. This allowing for near real-time replication and transformation into a purpose-built data store. Data is now being queried without impact on the source database since the data is being queried in S3, not the source database. This has enabled database transformation efforts and enabled machine learning that previously was unable to be done. Thank you, and continue to part 5 on purpose-built databases.